So since we have 300 households, the total of the system should have a peak demand of something like 300 kilowatts. So the wind is producing about a third of the needs of the system. Besides that, we have photovoltaic. We have assumed that photovoltaic increases their production when the sun goes up and then it decreases again. It's just an assumption and it's an input of the system. So the objective of this scenario is to illustrate the price variation. How will the price of the system react with the variation of the sun? And also identify how the load adapts to the price variation. The third scenario is actually exactly the same as the previous one, except that we have two sudden drop of wind. So 2 times in a day we assume that there was wind and then the wind stops. The idea of this scenario is to see how is the system able to react to that. Because I remember you that we are in an isolated system and people will want to adapt their consumption to the price they are actually paying. This scenario, we have put it into a video that I want to show you. So the video, which you see here, has the price and the quantity. So it's the price and the quantity diagram. In green, you have the offer. So the offer at €1 is the wind turbines. They're offering a very low price. But the system price, you see, is actually higher than 1. And the other green light there is actually the diesel. The diesel engine offers a lot of energy, but at a high price. And you see the load curve is actually changing throughout the day because the needs of the people to consume energy changes from 6 a.m. here, and you will see later at 12 a.m. or at 12 p.m. it changes, of course. The red point corresponds to the system, and we have here, for example, a price which will be about 20, and a quantity consumed which is about 150. Now we are at 9 a.m., and you see that besides the 100 that was offered by the wind turbines, there is also a lot of power offered by the photovoltaic at a very low price. But now I said there is a sudden wind stop. So the wind stops, and you see that the price slowly increases. And this goes slowly. Why? Because the load adapt their behavior from one side, and because the batteries are also discharging. The battery is actually the little line you see there. We have assumed that we have quite a small amount of storage capacity. So now you see we have still very limited wind, and the wind is again increasing. The wind is increasing, the price will again decrease. But it doesn't decrease at €1. It's actually a higher price, and the difference between €1 and the system price is money, of course, that the producers get in their pocket. There is a second wind drop, again at the end of the day, but now there is no more light, so there is no output from the photovoltaic. So the price goes through the roof. We are at the maximum price, and actually people have no other choice to accept a very high price. We arrive at the end of the day, and so that was the simulation for one whole day in case of scenario 3. So let me show you that on some graphics. First graphic, the system price. As I told you, scenario 1 in blue, fixed price. Scenario 2 and 3, exactly the same, except that we have at 2 times of the day a sudden wind stop. And what do you see? Of course, that the price is actually decreasing. I mean, the price is low, and in one case it increases to a maximum because there is no more wind, while in the other case it remains actually quite low. The total system consumption, so it's the consumption of the whole 300 households, is following a certain logic where there is a high consumption in the beginning. So I told you previously, I will explain you why. Well, the reason why is that the initial situation, the initial conditions of the hot water tanks is variable. So some of them are actually almost empty, and they're going to consume energy to fill up in the beginning of the day. So that's why we have a high consumption in the beginning, and then it's kind of normal. That was for the scenario 1 in blue. For the 2 others, we see that actually people are consuming very differently than in case you have a fixed price. They consume very differently, and they're actually following the availability of energy, of cheap energy in the system. And it's actually the opposite curve, almost, than the curve of the price. When the price is high, people consume little energy. When the price is low, they will consume more. And you see the difference between the green and the red, which is between scenario 2 and 3. You see that the price difference, the consumption difference is very high. That means that people adapt their consumption in function of the availability of the wind. Just to go through some more details, which are the loads that are actually participating the most to the variability of the consumption? Well, we can see here that warm water accumulators, the tanks, are actually participating much more than the light. As I told you, a light, when you get back home, you want to have light. You don't care that electricity is expensive or cheap. You will still switch on your light. So the variability of the light is actually much more small. There is a variability with the assumption we made, but it's smaller than with warm water, where we see typically the red curve, there is a sudden drop at the moments where there is no more cheap electricity. This is another last graphic to explain you the three scenarios. The energy stored in the batteries. So this is the sum of the energy stored in all the batteries of the system. Scenario 1 is not illustrated because we assume there is no battery. But scenario 2 and 3, you see that in the beginning it's the same. And the batteries tend to fill up because energy is cheap. But in one case, actually the energy starts to become more expensive. That's the red curve, scenario 3. And suddenly, the batteries will discharge. Same kind of information in the information of the energy stored in the warm water accumulators. The measure we take them is the average temperature of the hot water tank. We see, of course, a difference between scenario 2 and 3, between the red and the green curve, where in one case, the temperature will tend to decrease because the wind stops, and in the other case, we don't see that. So I leave the word to Vincent for final conclusions, and then we open the floor for questions.
Okay, so to sum up, the context of this presentation was that global warming will be there, for sure, and there is something to do about it. That in the future we expect that the power consumption flexibility will play a role. And then, what role exactly? The role will be has been investigated in that simulator, and we have shown that simulating 300 households in a realistic way can lead to adaptation in behavior, and in fact leads to a system that works. D-Power, our simulator, is able to reproduce a typical load profile. So that's the case number 1, where we see that in fact this is realistic. The load profile that we get when we have no flexibility is exactly the load profile that we have today and that we can measure and that is available on the web. Then we can model interconnection and introduce flexibility. Then is it realistic the way we model the flexibility? That's another question. We have tried to make it the most realistic. But in fact, there are, of course, places here for change. And then we are able to investigate different scenarios and stress test our system by setting the wind to 0 or setting, for instance, the storage of the battery to 0 and see if it still works. Of course, there are a lot of challenge and lots of assumptions that can be challenged in this work. For instance, we have seen that the flexibility that we have in the system, and that helps a lot, is coming from the warm accumulator. But in fact, everybody knows that it's not very interesting to heat the water just like that straight from electricity. And so maybe that would not be really an ecological way of doing it. So where could the flexibility come from? There are already other options.